Hello everyone, welcome to our engineering physics series. I am Assistant Professor Suresh from Vignan's Nirula Institute of Technology and Science for Women, Guntur. Do you know what is common between the screen of your mobile phone, the capacitors in every electronic circuit, the insulation in a transformer, and the gate oxide in a computer chip? They are all made of dielectric materials. Dielectric materials are everywhere in modern technology. Without understanding them, you cannot design a capacitor, build a transistor, or even make a proper cable. Today we begin our deep dive into the physics of dielectrics. In this first video, I will explain what a dielectric is, why they are important, and where they are used in engineering. Let us go. Let me give you the clearest possible definition. A dielectric is a material that is an electrical insulator, meaning it does not conduct electricity. Its electrons are tightly bound to atoms and cannot move freely. But here is the key point that makes dielectrics different from just any insulator. When you place a dielectric in an external electric field, something special happens inside it. The positive charges, the nuclei, shift slightly in the direction of the field. The negative charges, the electron clouds, shift slightly opposite to the field. No charges actually flow, no current, but the charges shift from their equilibrium positions. This shifting of charges is called polarization, and this is the most important property of dielectrics. Let me give you an analogy. Think of a group of people standing in a field. Normally, each person stands in their own spot, no net displacement. Now a strong wind blows from the left. Everyone leans slightly to the right, but their feet stay planted on the ground. Nobody actually moves from their position. No current flows, but everyone has shifted a little. This leaning is what we call polarization in a dielectric. Let me list some important examples. Glass, mica, porcelain, rubber, distilled water, wax, paper, plastics like polythene and PVC, and ceramic materials like barium titanate, BaTiO3. Notice that some of these are solids like glass and mica, some are liquids like distilled water, and gases like dry air also act as dielectrics. So dielectrics can be in any phase. Also notice that I said distilled water, not tap water. Tap water contains dissolved salts which make it slightly conducting. Pure distilled water is actually a very good dielectric. Now let me tell you why dielectrics matter so much in engineering. This will motivate you to learn the physics deeply. Application number 1. Capacitors. When you insert a dielectric between the plates of a capacitor, the capacitance increases by a factor of epsilon r, the dielectric constant. This is the most basic and important application. The formula is C equals epsilon r times C naught, where C naught is the capacitance without the dielectric. A parallel plate capacitor without a dielectric might have a capacitance of say 10 picofarads. Insert a piece of mica with epsilon r of about 5.4 and the capacitance jumps to 54 picofarads, more than 5 times the charge storage for the same size. Application number 2. Transistors and microelectronics. In every MOSFET transistor in your computer chip, there is a thin layer of dielectric material called the gate oxide. The performance of the entire transistor depends on the dielectric properties of this thin film. The semiconductor industry spends billions of rupees researching new high-K dielectric materials to make faster and more efficient chips. Application number 3. Transformers and high voltage insulation. The insulation in transformers, cables and power lines are all dielectric materials. They must withstand enormous electric fields without breaking down. Application number 4. Communication systems. Dielectric materials are used in optical fibers, dielectric waveguides, antenna substrates, and radar domes. The way electromagnetic waves travel through these devices depends entirely on the dielectric constant. Application number 5. Energy storage. Some special dielectrics like barium titanate are piezoelectric. They generate electricity when pressed. These are used in sensors, igniters, and ultrasound machines. Let me summarize. A dielectric is a non-conducting material that gets polarized in an external electric field. Charges do not flow, but they shift from their equilibrium positions. This polarization is what makes dielectrics enormously useful in capacitors, transistors, insulation, and communication systems. In the next video, we will define dielectric polarization mathematically and understand the concept of electric dipole moment. These are the building blocks for everything else in this chapter. Like, subscribe, and I will see you in video 2.